Hello and welcome to another Coding Casual coding project. Today we're going to code Conway's Game of Life. Now what you can see here on the right hand side is the finished product of what we will build in this first video. Now there are many videos on YouTube on Conway's Game of Life. So here I will have two videos. The first one will do the regular game, and the one after that, that's when we'll deal with different colors and different versions of the base game. Now, if you haven't heard about the base version of the game, Conway's Game of Life, let me quickly introduce you to the game. For all those of you who already know what that is, you can skip to where I start coding. Now, Conway's Game of Life is what's called a cellular automaton. Now, the idea is that we have a grid with a bunch of cells in that grid. And every cell that is alive is black and everyone that's dead is white. Now, if at any point, let's pause this here quickly, a cell is currently alive, it's going to ask itself, how many neighbors do I have that are alive? Now, every cell has up to 8 neighbors. Top left or northwest, then top north, northeast, east, and so on. So 8 neighbors all around. And it's going to count how many of these are alive. So this cell right here would say, this one is alive, so is this one, so is that one. So I have 3 live neighbors. And 3 here is a special number because one of the rules of Conway's Game of Life is that a cell like this one here that is currently alive has 2 or 3 neighbors, it's going to stay alive. If it has less than 2, it's going to die because it's lonely. If it has more than 3, it's going to die because of overcrowding. So if it's 2 or 3 neighbors, then this cell is also going to stay alive in the next period of time. Now, a cell that is currently dead is going to ask, how many neighbors do I have that are alive? And if it has exactly 3 live neighbors, it's going to come to life in the next period, even though it's currently dead. So let's quickly pause this. And let's go down here. So let's have a look at this cell right here. It has 1, 2, 3 live neighbors. So in the next period of time, this cell right here will come to life. And there we go. This is the next generation of the game. It has come to life. So it's really only these 2 rules. And you can have the most interesting patterns arise from this. So here we have what's called a glider cannon. We have some action in the middle, 2 solid blocks here, which don't really do anything unless another cell right next to it comes to life, because only then will this block do with something. Otherwise, it's just going to be a perfect still life. And then down here, we have these little gliders, which will go down here. Now, this is Conway's Game of Life, and on YouTube, you will find many implementations of this, but here I'm coding all of this in Python from scratch using a tool called Trinket, which allows you to code in the browser without having to install anything. And the way that I have done this here is I can pause and unpause this. So notice down here it says running and paused. And while we are pausing the game, I can add new cells right here to sort of change everything up. So if I add some cells here, everything's going to go in a completely different direction. This glider gun here is not going to work. And the whole idea is that we have a flexible tool that we can play around with and have lots and lots of fun with. Now, anyway, this is the introduction to this video. So if you were interested, keep on watching. Let's start with Conway's Game of Life. We'll start by importing processing. This is not a surprise, I guess. So from processing, we'll import everything. And we will, as with many other videos, also import the random module. We'll first define the size of our grid, which is really just how wide / how tall our output canvas over here will be. And here, I'm not going to set that to 600 pixels for now. We'll then have another variable, which is the number of cells, and we'll set that to 30 initially. And then we'll, from that, derive the size of the individual cell, which I'm just going to call cell size. And here, all this is really just dividing grid size by the number of cells. And yeah, with that, we can now define our grid, which we'll use a list comprehension for this. So we'll say that there is a cell object, which is yet to be created. And in this, we'll input row and column positions, and we'll have that loop over. So for every column in range n cells, and then we'll do that once more for row in range n cells. So that's really how we can create a grid of cells, except that we haven't created the cell class. So let's do that next. So what I'm going to do here is I'm going to define a class called cell. And you know what? I'm actually going to declare or create the grid afterwards, after we have created the cell class. Now the cell class is pretty straightforward. We'll have our initialization function, and we'll say that every cell has a row and a column. This is, after all, what we're doing here. We are using a row and column to create the cell object. So we'll have the row and column going into here, and then we'll say self.row is equal to that row, and self.column is equal to that column. And every cell initially has a, well, it always has a state, and initially that state is dead. So we'll just use a string here. You could also make this a Boolean true and false for being alive or being dead. It doesn't really matter. I'm just using a string here. And then we'll say self.nAlive is equal to none. Now, what is nAlive? nAlive will be the number of alive neighbors around that cell. This is going to be important later down the road when we'll have that state switching between being dead and alive. But for now, that's all we need. So we have our cell and we have a grid. So let's see if that runs. Let's click run. Obviously, we don't see anything, so let's print that grid. And there we go. So right down here, it has printed a lot of different things. So it has printed out a grid. So let's have a look at an individual cell. So let's go into the top left corner. So we'll say row 0, column 0. Let's run that. And now it's just giving us a single cell. And from that cell, we could now print its row, which is 0. We could print its column, which is also 0. So that appears to be working. Okay. Let's create ourselves a little function to visualize a grid or to show a grid. So let's call this function show, and it's going to be a function of a grid. So def show. Now in this function, we'll just have a loop for every I in range n cells, and for every j in range n cells. Well, what are we going to do? We'll get that cell from the grid. So we'll index our grid position I and j. And then we'll say if the cell's state is equal to alive, in that case we'll draw it one way, and otherwise else, in that case we'll draw it another way. So if the cell is alive, then we'll just say it's going to be black, so fill is equal to 0, and otherwise we'll just set it to 255, and we'll have a stroke around that, so we'll call that stroke weight. And we'll set that, I think 2 is probably going to look just fine. And then we'll create a rectangle, which is what we'll be drawing anyway, regardless of whether the cell is alive or not. We're drawing a rectangle. The question really only was which color we are going to use, right? So here we'll now say a rectangle cell.row times the cell size. This is the x position, so how far are we going over to the right? And okay, no, this is not making any sense. So this should be the column, I think, actually. How far are we going over to the right? And then we have cell.row times cell size. This is the y position. And then the width and the height of our cell size, because everything is a square. Okay, now that we have that, let's have our actual processing loop. We have setup, and then we'll say size, well, the width and the height are both equal to grid size. And what we'll do, we'll have a background, which we'll make perfectly white. And then we'll show the grid. So show grid, then we'll have our draw function. Right now, we don't put anything into here. Well, let's run this and see if that works. So I'm running this, and there we go. We just got ourselves our grid. Let's make this a little bit smaller, maybe only 400 and maybe only 20 cells. Run this again, and there we go. So these are now our cells. Okay, so let's have some function that we can use to activate these cells for us to be able to click on, one of the cells and then have it become alive, have it turn alive. So we can do that using the mouse pressed function. So define mouse pressed. Here we'll say I is equal to mouse x divided by, so you can use mouse x, which is just a reserved variable name in Python processing mode. And this will just record where the mouse is in terms of how far it is to the right or how far to the left. So this is just the X location of the mouse. And we'll divide that by cell size, and then we'll do the same thing for the Y location of the mouse. Divide that by cell size. And now we can index grid at this particular position. I'm not really sure whether I'm getting my rows and columns right here, the I and J part here. So this should really be, you know what? I'm going to make this Y, and this is going to be X. So I is the row and J is the column index, which is why I have to refer to Y here and X here. And now we are indexing this row and column wise. I think that's the trick. We'll have to see in a minute. So grid ij.state is equal to dead if that particular cell, if that already was alive. So if that is equal alive, then we'll set it to dead. Otherwise, this cell will come alive. And then we'll say show the grid. Because if we don't show the grid after we change the state, we'll still see what we had before. So this is why we have to have show grid down here. So let's run this once more and let's make a click. And unfortunately, it's not working. So what is the problem here? I'm going to pause this. So maybe, just maybe, I have to show it all the time in the background, in the draw loop. So let's run this. And it's still not working. So that did not fix the problem. So what I'm going to do is, let's just see if this thing actually works, if we are actually within the mouse pressed part here. So I'm just going to say, I'm going to have to debug this. So I'm going to say print here, and every time I click, so mouse pressed is not working. Why is that the case? And oh my God, the answer is so simple. Run came after mouse press, so it was up here and it has to go down here, otherwise this is not going to work. So let's remove the print statement here. Let's run this again, and there we go. So now I can click on some cells and I can make them come alive, and if I click on them again, they disappear. They are now dead. So this is working. We are now having cells popping up, or they are always there, we're just making them come alive. Okay, so there we go. We can create cells, we can switch them on and off, and we can visualize the whole thing. So I guess really the next thing would be for us to have some kind of function which advances our current population of cells into the next generation. I'm just going to call that update. So we are updating our grid of cells. Now, how are we updating everything? Well, every cell has to look at its neighbors and has to count how many of them are alive. So I'm going to call this have each cell look at its neighbors. And then we'll just have a simple loop. I can copy this from up here. So for I in range and cells, and for j in range and cells, grid ij, we are grabbing the current cell. And then we'll say if, well, we'll just define a bunch of neighbors. So neighbors, that is equal to, and I think the best way would be to have this in a separate function, which I'm going to call get neighbors of that cell. So we'll just say grid I and j. So we'll have some kind of function into which we can paste that grid and then a certain location I and j, and this function will then spit out all of the neighbors associated with these indices. Okay, so for example, if we are in 0, 0, it should then spit out 0, 1, and 1, 0. And if we are down here, it should spit out a full set of 8 neighbors, because around that cell we have a full 8 neighbors, whereas up here we only have 2 neighbors. And that is what this getNeighbors function will have to take care of. But for now, I think we are happy with that. And then we'll say cell.nAlive. That is what we had up here. Now we are counting how many of these neighbors are alive. Well, that is equal to the sum over the state of a neighbor, if that state is equal to alive, for every neighbor in the newly created list of neighbors. Alrighty, but well, let's first create this cool getNeighbors function. And we'll do that, right up here. So we'll say define get neighbors. I gotta spell this correctly. Get neighbors. And we said that we are going to be using grid, I, and j for this. And now, how does that work? Well, let's first grab the cell. We had that before, multiple times already. And now we'll define a north neighbor, a south neighbor. We'll have, well, west and east. And then for the ones that are like right in the center, we also have to have a northwest neighbor. We gotta have a northeast neighbor, a southwest, and a southeast neighbor. So yeah, potentially up to 8 neighbors for every cell, right? Okay, the north neighbor is really grid ij. We can use that for every cell. But with the north, we now have to subtract 1 row because we are going upwards. And with south, really the same thing. We're just adding 1 because we are going down. Remember, in Python processing mode, we're always starting. It's the same thing as if you were using the regular processing in JavaScript. We are starting in the top left corner and then counting downwards and to the right. So south is going downwards, that is adding up. Now west and east are not affecting the I index, but the j index. West, we are going to the left, -1. East, we are going to the right, +1. And now with northwest, we're just combining north, which is I -1, with west, which is j -1. And now northeast, well, here we are now adding +1 to j. Now comes south, which is +1 and j -1, and southeast, southwest and southeast. Here, plus, and another plus here. Alrighty, there's just one problem with this. I mean, this is perfectly fine for most of the cells, but if we are up here in the top left corner, as I just explained, and obviously there is only the southern neighbor and the eastern neighbor. There is no western neighbor and there is no northern neighbor to that cell. So we got to make sure that a northern neighbor only exists if you are not in the topmost row. So here we'll just say if I is greater than 0, else none. If you are in that top row, if I is equal to 0, there is no northern neighbor, so we'll just say that this is equal to none. And this is now similar for the southern neighbors, because if you are in the southernmost row, there's nothing coming underneath that, okay? So if I is less than n cells -1, and then it's just none otherwise. So with west, we're not just checking if j is greater than 0, else none. And here, I can just now copy paste this and replace I with j. Now with northwest, northeast, southwest, and southeast, we now have to combine these two statements. So north, which will require us to have I is greater than 0, and south, it's going to be this. So let's take this. Now we got to add and to each of these statements because we're always checking two conditions now. And well, let's take the west here. J is greater than 0. J is greater than 0. East, got to take this. Can copy this down here and grab west once more. J greater 0. Put this up here. And now we can just say else none to all of these. So else none, else none. Okay. This was a lot, I know, but how can we actually test this? Well, I think the easiest way for us to make sure that our code is correct, we'll just use this getNeighbors function. I'm just gonna use it down here in my mouse pressed function. So what I'll do is I'll say right up here, I'm gonna say grid 0, 0. No, actually, what I'm going to do, I'm going to go down here into the mouse pressed part, and instead of, making a cell come alive and showing the grid, what I'm going to do is I'm just going to say get neighbors off the grid at the ij location, which we just determined from the mouse location. And then, well, we got to have the function do something. We'll just say, well, right now it's just, individual objects. So let's create a list, neighbors, which will contain all of the different neighbors. So north, south, west, east, northwest, northeast, southwest, and southeast. And then it's going to print the neighbors. So let's see if that works. I'm going to run this. I'm going to go click up here, and it says that it found 1, 2, 3 neighbors. Now that's rather interesting because it should really only be just one neighbor. Oh, no, it's 3. Yeah, right. Oh my God, how could I forget? I always said it's 2, right? It's got to be 3. So if you're in the top left corner, obviously you're also going to have that square down here. Geez, I always was thinking of just going like straight, but you can also go diagonally. Oh my God, big mistake here in my thinking, but the coding was actually fine. Oh my God. Now anyway, 3 neighbors, so that should work. So the first one is none, which would have been the northern neighbor, so that's fine. Then comes a cell object, which is the southern neighbor, that exists. Then comes another none down here. This would have been the western neighbor, which does not exist. The eastern neighbor, this is a third object, which does exist. Now comes 2 nones, which is northwest, northeast, neither of which exist. Then comes another none, which is southwest. Obviously, if you're in the top left corner, go in southwest. It's not going to yield anything, but go in southeast, which is this down here, will give us another neighbor. So I think this works. So let's go down here in the bottom right corner. And now it says list index out of range. So yeah, maybe there is another bug in this. Southwest. So the problem is I forgot about this -1 part here when I copy pasted this. So this has got to be -1. So let's run this again. Top left works and bottom right now works as well. So I think we're fine. So let's pause this. Get rid of this print statement here and revert all of that down here like this. And yeah, so once we have our neighbors, we'll now return for every, well, we only want to have the neighbors that actually exist, right? We don't want to have the none statements in here. So the none statements, they don't exist, right? We don't want to have them. So what we can do here, we can just say return neighbor for every neighbor in neighbors. So return every element in that list, but only if neighbor is not none. So only return a neighbor from the neighbors list if that neighbor is not none. So yeah, now our getNeighbors function should be just fine. And so we can now use this function down here. And once we have all the neighbors, we are using the sum function over that list. Remember down here we have another list comprehension. We are looping through that list of actually existent neighbors, and then we are checking whether their state is equal to alive, and if it is, we are increasing our cell and alive counter. And yeah, once we've done that, we can now update each cell depending on its neighbors. Now you might be asking yourself, well, why aren't we doing that in one step? In one go? Why are we even having this n alive thing? Why can't we just count everything and then without having to like change the cell object, change one of its properties, already update the cells? Well, the problem with that would be, say this cell is coming alive because it has a certain number of neighbors around it that are alive. Well, if we are changing that and then advancing to the next cell, it's kind of like, you know, we are now asking, well, how's your neighbor doing? Which asked, how are you doing? And this would kind of like bite itself, you know, in the tail, really. So that's not going to work. So what we got to do here is we have to first define or like sum up or count the neighbors for every cell, store that somewhere, and we are storing it in the cell class itself. And now we are making the decision on which cells come alive and which ones die for all of the cells in our grid. Now, let's loop through our grid once more. So let's copy paste this. And now we'll say if the cell.state is equal to alive, we'll say if you have less than 2 neighbors, so if cell.nalive is less than 2 or cell.nalive is greater than 3. Now in that case, we'll say cell.state is equal to dead. because, well, you're dying of loneliness or overcrowding, right? These are the two main rules of the Game of Life by Conway. And if you are dead, so else, so we are now in that outer if statement. So if you're dead, there's one way for you to come back to life, which is if you have exactly 3 neighbors. So if n alive is equal to 3, cellular state is going to be alive. And then that's really all we have to do here for updating our grid. This is all happening in place, so we should be just fine with that. So we have our update grid function. We have a function to show a grid. This was just sort of a helper function, this get neighbors thing. And now down here in our setup function, we don't have to change anything, but in the draw function, this is where the action now happens. So what I'm now going to do is I'm going to introduce the running variable. So I'm going to have another variable. Running is equal to false, because initially nothing's happening, but if I click on one cell up here and it comes alive, it will immediately die already, like right after that. That's because if frames are happening at an insane, if frames and therefore generations of the game are happening at an insane level of speed, I'm going to create that cell, and then it's going to look around, find, oh, I don't have any neighbors, I'm going to die of loneliness, and it's instantly going to disappear. So what I'm going to do is I'm going to have a variable which is whether or not the game is actually running and advancing to the next generation. And I'm going to set that to false, which means I can make multiple clicks without the game advancing to the next generation. And only once I've done that, and I'm hitting a specific key, or really any key on the keyboard, that's when the game will start, and only then will the cells start looking around themselves and determine whether or not they will die or come to life, whatever. So running is equal to false. And now down here, only if the game is running, we'll say that all of this is happening all the time. So the background and show the grid, but in between here, we'll now update the grid. Okay, now how do we turn running on and off? Well, we can do that using a simple function called key pressed. So there's mouse pressed and key pressed. So we'll now refer back to the global running variable. We are now changing that variable. That's why we have to use the global keyword here. So if the key is equal to nothing, that's how you can refer to the space bar. You don't have to do that. If you want to have any key do that, that's perfectly fine. But I just want to have the space bar to be this pause and on-off button here. Okay, hard word. No, anyway, if the key is equal to the space bar, then we'll say that running is equal to not running, which means this is going to work both ways. So if it's false, then we're just going to set it to not false, which is true. And if it's true, we're going to set it to not true, which is false. So this will work both ways. And then we'll say if you're running, so if we have just set it to true, then we'll say print running. This is just going to help us. So if we are doing stuff here and nothing's happening, this might just be because it's paused, and then we'll have this print statement whether or not it's running or if it's paused. So print paused. Oh, typo. And let's do that. So I can now click and start the game like this. Well, it's not started yet. I just created a bunch of cells. But if I now hit the space bar, the action happens and the game is now running and the game is evolving up here. Now the game has come to this particular state here, which is a solid block. This is not changing anything. Remember, I said this before. This cell right up here has 3 neighbors, and every other cell in this block has 3 neighbors. So yeah, they are not changing, but none of the cells around the block are coming to life because this cell right here is only 2 neighbors. This is only 1. So they only have 1 or 2 neighbors. They will never come to life, and this is why the game, regardless of whether or not it's paused or whether it's running, it's not really changing. To restart the game, we'll now hit stop and run again. So let's create some cells and see if we can create some interesting objects here. So let's run this, and there we go. We have some sort of evolving structure. And yeah, there we go. Let's pause this for a moment. So, oh, this looks really interesting. Nice symmetry here. And this one here is one of the common oscillators in the Conway Game of Life, because, let's run this, you can see how it's just constantly switching back and forth between its two states. And maybe, yep, just here, new blocks came in or new cells were activated coming in from the bottom. And now this regular pattern, which was just self-repeating itself all the time, has been broken up and changed into this. So let's run this and enjoy the show for another couple of seconds here. And I think this is now a very good point in time to end this first video. We have recreated Conway's Game of Life. We can pause the game, add in some additional cells because sometimes the game settles on a solid position and doesn't really change after that. And then we can hit the spacebar once more and the game will restart after that. Now it's time to start with different colors. This is very interesting. We'll also have a look at some of the most interesting patterns that are to be found in Conway's Game of Life. And yeah, but that'll be something that I'll do in another video. Have fun watching that. And if you like this video, please consider subscribing to the channel, leave a comment, and most importantly, tell some of your friends about this channel. Thank you very much for watching.